Thank you for being here. I'm very happy to be in person. It has been a while since I was in a Python conference in person. So my name is William, and I work at GitLab. I am also teach in a Czech university, a course that is called Machine Learning Applied, which is basically now being called MLOps. So among the different things that I do, I like to share knowledge, and I am thrilled to be here because it's super cool when you can learn something and then come to a super friendly community and just share something that you learned that might be helpful for someone else. The idea and the way I want to structure this presentation is in a framework that I usually follow with my colleagues or my manager. That is, first, let's ask why. Why should we do this? Like, why are you here? You have some interest in Python machine learning, I assume. So, and how? So in this case, why was I doing what I'm about to teach you, how I did it, and what we used. So what was the goal? At work, we had like in real life, we had a highly imbalanced data set. Basically, we had to predict one event that it was so rare that we have to model it as an anomaly. So it's not the classical thing that you can find in Kaggle that you have a nicely structured data set. No, this requires a lot of patience, a lot of SQL, a lot of creativity, and even read and refresh statistics theory to try to find a workaround. What can we do with this? And so that was the status. We had this super imbalanced data set, and we have to predict anomalies. So here is where things started to be fun. And this is something that you can find today everywhere. And probably if you ask these tools of today to generate code, this will be probably the most likely output that it will create for you. So what was the thing? When at work, we said, let's just follow the recipes. Let's try a simple baseline algorithm, and then we take it from there to start improving. And even if we change the algorithm, like the one that we were having here, there is something that has been some sort of a footprint when you start doing hyperparameter tuning. Is that first you define the hyperparameters, and once they are defined, then you run them. So what happens here, if you see to your left, right, it's a person, the one that has to say, for example, for this classifier, what are the numbers of estimators, the minimum sample set, the leaves, and so on. So this is something that a person will define, and if you ask anyone, how did you come up with these numbers? What do you think will be the answer? It was like that in the documentation, or I saw it somewhere, or I did it once and it worked, so let's try. But it is completely esoteric. No, there is not really a reason why I can say that I tried this. What if I am very far from the actual number that will make my model or hyperparameters be the best for my model? So then we started researching, because also it brought more problems. In this case, we were seeing that the model that we were training, 1% was great. It's not like the competitions that we say, oh no, it has to be 99%. No, if we could increase 1%, one of the metrics that we were defining, it was translated in the hundreds of thousands of dollars. So we said, we don't need to be picky. We don't need the extreme accuracy or so on. What we need is some improvement. And that's when we saw that even degrading the model will cost money, and just us working on this, running it in different infrastructures or in our own computers was impacting negatively the finance of the model, the training, and so on. And it was very annoying because it was too long to find these hyperparameters and to train a model. So just in case, a friendly reminder is that when I talk about hyperparameters, this is what I was mentioning, that is what the human will set, and a parameter is what the model learns. Just in case, friendly reminder. So it's important, this word, because this is how the core of how we solve this problem. So nowadays, what maybe not you, but many people do, is that they jump to start trying different numbers, as we said, because they find it in documentation or someone has told them or it worked before. So this is a manual task. What you do is just changing things, hard-coded, and then putting it into a learning algorithm and hope for the best. And this is an iterative process that it can take different trials. And one of the interesting papers I was reading recently is that by having a human or data scientist in this case tweaking hyperparameters, you are somehow biasing the model because you are seeing the output. You know it's not working, so let me change this number. So indirectly, you are contaminating your metrics because you already know what works, and you are inputting something that you believe will do it better. So that probably can affect the way in which your model can generalize. So there must be a more efficient way, one that doesn't introduce that much of a bias. And this is where Googling and finding something, we found a paper, research paper, where there was a team that they were addressing all these problems that I mentioned. They were saying, we want to create a way in which you can use a hyperparameter tuning library that will catch up with the software architecture of the models. Because I don't know if you remember in the early days of TensorFlow, you first have to define. You have to put placeholder, everything in the network, and then you can run it. And this is how the other hyperparameter frameworks they were today. They were, I don't know, it has been improvement in this, but they said, what if we do it in a define by run, not unrun? So that was the first architectural difference, where we saw, okay, this sounds more like Arias or these other modern frameworks, where you can actually see in between what's going on in the tuning process, and maybe apply some early stopping or some other things. So in this case, so we found this library that we thought, okay, let's give it a try. And what it does is that it will automatically, you define some ranges, and then it will automatically do the hyperparameter tuning for you, and it will use from in the back end of it. You can read the paper. It will use some other techniques and combinations of them that are better than you just guessing. There are, for example, Bayesian optimizations saying, okay, this one doesn't look promising, so I better prune this trial, and so on. So at the end, what you can do is that you start making this automatically. So I told you what was the problem, how you can solve it by using a hyperparameter tuning library that has a different architecture, and now what? So it's very intuitive, and I will say easy to understand the main recipe or the main concept. So the first thing that you do is that you take your learning algorithm, whatever it is. It can be random forest, XGBoost, like in this case, even a neural network. And then you take this learning algorithm and you wrap it in a function that you will call up the objective function, which is also cool because if you are more purist and reading more the theory of ML, we are always trying to optimize a function. And this optimization can be either something has to grow, something has to decrease, but has to go in some direction. And whatever direction makes sense for us is good. So what we do is that we define an objective function, and then we pass an object that is called a trial. And we wrap in this. This is basically a wrapper, when you put the learning algorithm there, and then you start running the optimizations. So this is the main idea. And this is why it is so easy to start, because you don't really have to break your code. You just have to, okay, this is in the part of my code where I have defined the model and where I have where I need to start passing hyperparameters. So I'm gonna just use this wrapper and put it there. So more closer to how it looks like. So first, the 3 steps for this recipe is you import Optuna, you wrap the algorithm in the objective functions, and then you run the optimization. How does this look like when I take some examples from actual code? So basically here you can see in the code part, when you import a library, you can use this wrapper, def objective, and trial. And what you are doing here is very important. It's because when you see in the dictionary of hyperparameters, what we do is that we start replacing everything that was hard-coded before with a method that is called suggest. This is what is called the suggesting methods. So only thing you need to know is you're suggesting an integer or a float. And then you will let the library to run these suggestions and to run these values of hyperparameters, and then return to you, and then create a study, which is the part that is below. And this study is gonna say, okay, I am now taking, I'm doing a sweep, I'm sweeping, I'm running these hyperparameters through this, I'm doing the hyperparameter tuning, and now I'm gonna do it for certain amount of time, which is the trials that we can see there in the back. So this is the main recipe, and one of the things that is very convenient is that by learning these 3 steps, you can do it with different frameworks. This is just one example with XGBoost, but you could do exactly the same with PyTorch or other learning algorithms. So this is the recipe. And in more detail, so we define the objective function, which is the main wrapper was after you use the import Optuna. You need to, when you rewrite your code, you replace the hyperparameter values with the suggest method, and then you create a series of optimizations. That is what in the Optuna jargon is called a study. And with this study, we have the function optimize, where we will pass this function because this is the function that we want to optimize, and we tell in which direction. Do we want to maximize this value? In this case, I was talking about accuracy, so I want to maximize it, or you might want to minimize it as well. So different advantages that we also found with this is that, first of all, as I mentioned, is framework agnostic. But before I move that, this is quite difficult here with this screen. I want to show you how these things look in real life. So this is, I have prepared a set of examples in Jupyter Notebook, of course. I am more data scientist than engineer, although my background is engineering, but I like more, for these things, Jupyter Notebook is great. But I have a script that is not in Jupyter. So you see, here you see the things that are normal. You just import the data set, you do some bit of data processing. And the idea of this is that I'm using one open source data set. What you want to do is to predict who makes over 5,000 a year. And here you can see in practice how the execution of the different trials when I just wrap XGBoost classifier in the Optuna objective function. So this is one thing. This is how it looks when you apply, and this, let's say this is the hello world. And now what is another of the advantages that this has, which is where you can see the money savings. So I was saying that is framework agnostic, but it has this very neat feature that is called pruning. And what this does, and we saw it in real life, is that you can create, you can attach, let's say, a callback, which what it will do is that it says, it is going to, in the process of, or during the tuning, it is going to use some algorithm in the back that we can read in the paper what it is about, the TPE, that is going to say, this trial doesn't look promising, so I better don't waste time or cycles or energy doing this. So when you do that, and when you integrate this pruning callback based on the metric that makes sense to your problem, you can try again and train the algorithm, and you will see here, for example, that when it starts training, these ones, they look promising, so it is giving us what are the set of hyperparameters that we should use. But there are some of them that it says this was pruned, and then it will just keep in the value of the one that so far has the best hyperparameter values that you found. So this is one thing that is pretty neat, because here I was doing some tests for this presentation, and I could see that when you compare the pruned versus the non-pruned, there is a difference, sometimes like in 20 seconds, depending of the, not in this one, this is a very small data set, but the larger the data set, you see that the improvements are very significant. So in this case, this is a data set that has way more features, and the moment I run this, you see that the difference between one or the other, between pruning and not pruning, is 20 seconds. So now, in the real case where we're using this, we're using a data set that had 400,000 rows, and like hundreds of features. Plus doing more feature engineering, we add even more. So the difference here was very noticeable. It was in the range of hours of using the traditional grid search versus using this approach. That's when I said, this is cool, I'm gonna share it because I think it's a very neat library that more people should know about, and combine it with what they are doing in either framework. So the other thing that it is very important is that you can have also this idea of having the human in the loop. When you are able to visualize what the iterative process is telling you are the hyperparameters that are moving the needle, that are more important, then you can also prioritize what do you want to do, which ones do you want to let the algorithm, the library, tweak on your behalf. So this is one of the things that I believe is really cool, because it also helps you to understand and move with certain direction, saying, now I understood that this feature is crucial for this, so I'm better focused on this one instead of the other. And that at the end of the day also ends up in saving time and money. So that's one. The other one that I don't have a demo for this, but it's pretty neat, is that the concept of parallel execution. Basically what it does, it says that if you have a common storage, because you can parallelize this library, what you can do is that there is one common storage and one of the workers, each one of the workers, they will execute the calculations independently and they will put it in the storage and then they don't need the other one to continue. So you can also do this, and I have seen implementations of people with this and Kubeflow or Kubernetes where they have spread more the parallelism of this library to achieve even faster results. So one of the things that also I wanted to share is that these things are very cool in Jupyter Notebook, but there are more ways to optimize your life as a data scientist, if that's okay to say. So this is the same or a refactor, let's say, a script that I put in Jupyter Notebook in an attempt to make it more production ready. It's not, it's demo. And that we can put it into a CI or CD system. So another pain point for data scientists is that we want to use GPUs. Have you seen the news how the market of this, but everyone needs them. And it is very hard sometimes to maintain a machine with the correct drivers. That's painful. So one of the things that we are experimenting now in my team is that imagine that we have this code and we said we want, by the way, we are also suggesting code now. So I'm going to dismiss that suggestion. I don't want to load the data. But imagine that I made some change, and then I want to commit to the main branch. Don't only do this at home. Only commit to main at home. Don't do this in your company. This is a demo project. But what I want to show is that you saw that I changed something in the script. And then what I'm doing here is that this has CI integrated. So the first step is just checking the machine. It's okay. It can be a Docker file that is building the image where you need to run the training. And then there will be another step that is called train model. And this step, what we are doing here specifically, is that I told the CI that you have to use a GPU runner to execute this job when I'm going to train. And I'm taking advantage that XGBoost has a parameter that you can enable, the hyperparameter you can enable the GPU. So I'm taking advantage of that by providing hardware that is automatically enable the GPU, and I don't have to deal with drivers and so on. You can see here in one job that already finished that just out of pleasure I'm doing different things. If you have ever thought installing drivers, you know that this output here it means that you succeeded. When you write NVIDIA SMI and you can see this output, you say, yes, finally. So one of the things that I'm doing just out of pleasure is that whenever I run this job, I want to run this. I want to make sure that, yes, this ephemeral environment is seeing my GPU. And now I am installing the requirements, and I am running now the training that you saw in the Jupyter Notebook. So in this case, what I'm doing is that there is one script, Python script, that has all it's not Jupyter. There are people, and we do that as well, we convert Jupyter Notebooks to scripts, but also that's also prototype level. Ideally, you should refactor. And then what you see here is all the trials, pruning as well, all the things put together that we talk about. And then we have even more optimization, because what this is doing now is that this is a larger data set with larger number of trials, and we are using pruning, we are using GPU, and the best is that if you're a data scientist or anyone that is working with these algorithms, you just have to worry about changing the code, committing it, pushing it to remote, and then let the CI system to make the training for you, automatically enabling a GPU for you. There is a paper about the technical depth in ML systems, and one of the gaps where people lose and waste a lot of money is when you put someone 2-3 days to maintain a machine with GPU. In these cases, you don't have to do it. It will be automatically enabled for you, and you can continue experimenting. Now you can see here that the sky is the limit. I can add wrappers of MLflow, and then I can start pushing more experiments from CI and automating lots of the things, and either from Jupyter Notebook or refactoring code. So putting all together, this is story, that this is what we are doing nowadays. is that we switch to a define by run optimization for finding hyperparameter tuning. And then we start mixing the best of two worlds. We said, let's use developer workflows as well to also optimize our lives and optimize our workflow as a data scientist. Let's create a merge request. Let's use CI and CD systems if we want to deploy and automate the training of models. Okay, this is the, thank you, Jig, grazie. So I live in the Czech Republic, and Jig is thank you. But I am originally from Colombia, so that's what I put it second in Spanish. Thank you so much. Do we have, yeah?
Yeah, do have some questions on slide? Prova, okay. So we'll start with the questions. If we have time, we can take up some more. Okay, so thank you very much. Great talk. So I'll start with a question that you almost answered yet. So can I log the performance for every combination of hyperparameter in an elegant way with just Optuna? So you mentioned MLflow. If there is any other way to do that?
Is the question that if there is any other library like this one that we can do the same? Or is that?
I don't know if the person...
Oh. Okay. Yes, yes. They have their own. If you do dashboard, Optuna dashboard install, it will have its own UI where you can track the experiments. I say MLflow because it's another open source that not only the experiments, but you can also send the artifact or the model that we're trained to a model registry. That's what I mentioned in MLflow.
Okay, thank you. Is there a way to do nested cross-validation with Optuna?
Yeah, there is one. It depends on how you define in your code. But for example, in the first one, the example number 1, what I was optimizing was the cross-validation. So here you can see that I am using cross-validation score. And there is a function that is in charge of doing this cross-validation. And this is what I pass to inside the Optuna wrapper. So you can even add that layer on top of that.
Okay, great. Is Optuna able to run parallel runs on multiple machines or clusters?
Yeah, it is. And that's a demo that I am due to create. But yes, short answer, yes. And typical answer, it's in the documentation.
Okay, yeah. Thought so. How does Optuna avoid biasing the model compared to manual tuning approach?
Yeah, that's a very good question. One of the things that is not necessarily that it doesn't do it, because you like in this case, you have to define, like I did here, a range of the number of estimators. To some extent, you are doing it there, but the difference is that when it's trying from, let's say in this case, from 1 to 10, in the background, what it's doing, and I invite the person who has this to read the paper, because they show here all the different, these are the different techniques that they use to precisely say, how can we really choose the best based on the objective function and the things that I want to optimize by combining different algorithms that help you to find that value. So one of the things that they show here as a part of the problem that they want to solve is that different techniques, they use one algorithm, and this one can use 2 or 3 algorithms at the same time, and then define a logic to say, okay, following this optimization method, I'm based on the report history. They also offer something that is called report history. You can use the typical, based on the probability of what happened, some a priori information to decide what is the probability of what's going to happen next. So this decision by an algorithm is isolating you from that responsibility that you do when you do grid search of saying, oh, I just tried 2, now let's try a number 3, just because I believe. But that's not your decision, it's a decision that is made by a backend.
Okay, great. Last 3. So does Optuna support also automatic feature engineering, like dropping features or creating interactions?
Creating what?
Interactions. I don't know if the person asking the question.
If it supports feature interactions, like creating a feature out of two single features, because you show the hyperparameter optimization, but maybe sometimes you create the sum of the columns. Or
Yeah, I am not entirely familiar if it can do that, but what I know is that part of the analysis that it does is that it finds for you highly correlated features, and it can shut down some of them. They are too correlated. That's one thing that I know it happens in the back.
Okay. Have you tried other AutoML libraries? What are the pros and cons of the two approaches?
Okay, I haven't tried. I tried the previous ones that were designed and run, and this one fit perfectly our use case, basically because we are mostly data scientists, so we need basic Python skills to be able to tamper with the code, with the code and definitions, and this is pretty Pythonic in that sense. So that's why. But I am due to offer a comparison. The comparison that we made was using the traditional grid search versus this one, and when we saw that the difference was big and that translated to dollars, it was a lot, we said, okay, we need to deliver. We have sprints every 2 weeks. I take this one. So yeah, but it's a good thing, like probably for another iteration, to have some comparison with other libraries like this one.
Sorry. How the values of hyperparameters are chosen for a trial? Is there a dependency on the outcome of the previous trials, or is it at random?
Yes, it's the first option. There is a dependency. If you see in the process, it is keeping in memory what so far has been the best trial. And this is crucial at the moment of doing the pruning, because it will let you know based on priors and probability that if it makes sense to continue, because it is not at random. It is keeping a history of the thing that happened before.
Great, thank you. Okay, we have a last question then. How does Optuna travel in the hyperparameter space? Like, how optimize the objective function?
Yes, that's a very good question. And for this one, because I'm also running out of time, I know that you will find more joy if you read, for example, the definition of the algorithm and how it does it. I will send these links if anyone is interested.
Great. Okay.
Thank you so much.
You want a mic?
Or I don't need it.
We can talk outside if you want.
Just, I think the question is interesting and a bit further. Thank you for your presentation, Mateusz Sorocki from IT, machine learning engineer. So, I know that the Optuna and entire-based optimization is a game changer for our daily work. However, in a sense, you have a problem where you can specify a space of hypotheses like hyperparameters and a cost function like a total score or something. You can also think about it like you can use Optuna to think what can be your neural network structure of entire model. You can use Optuna to add some layers, delete some layers, add dropouts, and so on. And my question is if you use that in production, because I just only did that in a study, and if yes, what was the effect of that? If not, if you think it is worth to use Optuna to create entire models.
Okay, based on your example, the one with a neural network, this defined by run, I know that hyperparameter way is catching up with the way that you actually define the neural network when you use PyTorch nowadays or Keras. But I haven't tried it in production, so whatever I said, you saw me here committing to the main branch, so I haven't done this in production. For our use case, it makes sense because we do it as an experimenting phase in our infrastructure, and once we are happy with the model and we run batch, the predictions that we do are in batch. We are not doing any online inference that I can tell if, oh, this is affecting production or not. So it's every day we take the thousands of rows and then we pass it to the model, and next day we see how it went. So I am not qualified to tell you if that approach, which I know it is how it works in neural networks, what can be the consequences or the benefits of doing it in a production environment. So again, thank you for your question. That's something, food for thought to prepare for the next presentation of this one. Thank you.
Okay, time is over. So thank you very much.
Thank you.